What are the problems with what Jim Al-Khalili says about the slit experiment? Well, the first thing I want to start with is with some of the problems that we have with mathematical physics. So let me go over the summary. Let me go over the summary of what I'm going to cover today and how with Jim Al-Khalili, where he's going to fail. Okay, so this is going to be like a summary. I'm going to just give you a little introduction here on what he's going to be presenting. I want you to keep an eye out for these issues. These are the ones that underlie his talk. Okay, and here it is. First one, mathematical physicists dismiss physical interpretations as petty philosophy. They say that doesn't belong in physics. So the question is, why did the mathematical physicists, okay, attempt a physical interpretation to begin with if that's just philosophy, if physical interpretations are not part of physics? Okay, why didn't he just stick to math? And the answer is there, because otherwise his math is irrelevant to the real world. It has no purpose. Okay, so this is the issue. The issue is that on the one hand, they dismiss physical interpretations. They say, well, that's philosophy. That's the philosophy of physics or the philosophy of science. And then they all try to go in there to the public to try to explain what they do in physical terms. Okay, and they make a big mess of it. It's all irrational. And then when you question them about it, they say, well, that's philosophy anyways. Science is math, not physical interpretations. Okay, so this is the issue. Keep that in mind, okay? And the first issue is that they cannot explain with math. Math exclusively a descriptive language. You can only describe with math. And if you can only describe, of course, you cannot explain. Now you understand why in the last 400 years they have converted science into math, into descriptions, and we have no explanation, no rational explanations today. None. Not coming out of the mathematical physics world. That's why they are not physicists, because we need to understand, why the Earth doesn't fly out of the solar system. And they say it's warp time. And you say, well, that sounds irrational. And they say, yeah, we don't understand it either, but that's philosophy anyways. So don't ask that question, because you're asking the wrong people. You should ask the philosophers. What do? They send you to the mathematicians. They say, oh, they're the ones who know. They tell us. So that's where we got to run around, okay? Anyways, the physical interpretation part is inferred, and this is an important reason that mathematical physicists reject physical interpretations as a component of science. Mathematical physicists see it as an opinion, speculation, or belief. Okay, so because it's inferred, and they can't prove it, they can't tell you what's in there in that invisible world, and so they say, well, that's not science anyways. We have no way of proving it. That's their argument, in essence, okay? That's the first issue. Second issue here, rundown. Math phys simulate everything with particles. That's the problem. For the last 10,000 years, they've been using particles. Even when they use waves, they're doing particles. Because what is a wave? It's a up and down the oscillation of particles. Some say it's the oscillation of nothing. Fine, that's even worse. But they've always used particles. And this site is the first one for the first time that we have a different proposal than waves or particles. Okay, and obviously it's not wave packets or none of that nonsense from quantum. Okay, simulating the invisible atomic and subatomic world with particles inevitably leads to paradoxes. And instead of saying, well, we got a paradox, we have a problem. No, instead it's like Niels Bohr once said, oh, we've reached paradox. Now we have a chance of making progress. So they boast about it. They think it's good. Okay, and they mathematical physicists, they twist this around in their favor and proudly call them dualities. Okay, so if light is both a particle and a wave, if you can't, what other dualities are there? Well, they have tons of them. Really, they're all over the place, and a lot of them just have to do with interpretations, all on the basis of particles. That's the issue. That's the main one, the duality of wave-particle duality. Okay, they don't see dualities as defeating their theories, but rather as quirks of nature. Mother Nature playing incomprehensible tricks on them. So the question is, I'm not a great fan of Karl Popper. I think what he said is nonsense, okay? But these people believe in Karl Popper. And Popperian falsifiability, why didn't they apply this principle just now when they needed it the most? They needed it here to reject the particle hypothesis. Because if you cannot explain anything, absolutely anything, with particles, with discrete particles, then this is the moment that you have to apply Karl Popper and say, look, we can't explain the slit experiment. We can't explain polarization. We cannot explain, how the atom works. In other words, how the electron gets bound to the proton. That's the main issue, right? How does the electron stay faithful to the nucleus? They can't explain that with particles because you can't pull with particles, you can't attract. Then if they can't do, and you can't explain two magnets, one attracting another with particles, so if you cannot explain absolutely any of the invisible phenomena of Mother Nature's with particles, wasn't this a time to apply Karl Popper and say, hey, just one instance falsifies your theory. Here we have 10 of them. They all falsify your theory. So at that point, you had to reject the particle. You cannot explain anything with particles. Period. We're done. And they didn't apply Karl Popper there. They give lip service to Karl Popper. I don't know why, but then on the other hand, they never applied it to the particle hypothesis. Okay? And they should have erased the board and start all over again. They should have brainstormed new hypotheses, new mediators. Okay, which is what we did here. Okay, we have a new proposal on the table. Okay. Here's another problem to keep in mind. Actually, like 4 of them I have here. The 2 of them went by. Here's the third one. Third one is that theory is not a description. A theory is an explanation. Okay, I hope that's clear. Someone says, what's your theory? You're going to explain something. Oh, I think Johnny broke the window with his baseball bat. That's, I think, how the glass ended up on the floor. You're explaining something. Or how did this woman die? Well, she was stabbed to death. You're explaining something, how something happened. That's a theory. And it's not a description. If I describe a chair and say, yeah, it has 4 legs, 1 backrest, 1 seat, did I do science? Is that what science is? Just a description? If I measure and say, oh, this table measures 1 meter, is that a theory? Is that science? This is the issue. And quantum theorists admit, concede, and confess that all they have are descriptions of the invisible, microscopic, atomic, and subatomic world. That's all they have, descriptions. Mathematical descriptions. That's all math can do, describe. Math cannot explain causes, mechanisms. Therefore, they don't have a theory. There is no so-called quantum theory. The quantum theory, like Khalili just said a minute ago, is all irrational, illogical. So if it's irrational and illogical, you might as well put angels, spirits, God, black magic, whatever you want in there. Because he says it's going to be irrational. He doesn't have a rational explanation to give you, therefore he has no theory. He just says, yeah, bring your magic wand, this is how we do it in quantum mechanics. Yeah, no kidding. So you don't have an explanation. Okay, so if you don't have an explanation, you don't have a theory. There is no such thing as quantum theory. There's quantum description, and a description is not a theory. Keep that in the back of your mind. Okay, so that's what it is. All they have is a description, and mathematical physicists refer to these descriptions as theories. They say, oh, quantum theory, it's been proven, it's been confirmed, it's very accurate. Huh? What are you talking about? They're talking about measurement. They're talking about equations. They're not talking about theories. There is no such thing as a mathematical theory because mathematics cannot provide explanations. It's mathematical descriptions. That's all that mathematical physics does, the math part. The physics part is all irrational physical interpretations. which they dismiss afterwards and say, oh, that's philosophy anyways. Philosophy of science, philosophy of physics. They give service to rational physical interpretation, dismiss them as philosophy. Okay. Okay, and last but not least, but this is a serious problem also, I want you to keep this one also in mind. This one here, if I can get it. It's the issue that the general public is completely unaware of all this. The general public is hypnotized, blindsided, totally unaware that mathematical physicists have no understanding whatsoever how the universe works. And by that I mean explanation of the invisible, intangible agents and mechanisms. That's what I mean when I say explanation, theory. We're talking about mechanisms. What is the mechanism that Mother Nature uses out there to do gravity, to do atom, the quantum jump, to do light, to do magnetism, to do electricity? This is what we want to understand. The physical interpretation, the causes, the mechanisms. That's what I'm talking about, okay? The layman has been conditioned to accept everything on the basis of authority, that mathematical physicists can do no wrong, that technology is proof of theories, such as quantum mechanics and general relativity. The typical defenses are, you'll hear this all the time, we wouldn't have computers if QM were wrong. In fact, Al-Khalili says that same stupid thing. So it means he never learned anything in the monastery where he studied. Okay? Or we wouldn't have GPS if GR were wrong. Are we talking about GR description, or are we talking about the explanation? Are we talking about warp time? Is that what we're talking about? Or are we talking about Einstein's field equation? What are we talking about? Okay, so keep all this in mind, because this is where the problem is, especially with the slit experiment. And these rejoinders are irrational. They show a gross misunderstanding of the issues at hand and total misconception of the scientific method. These people have no idea what science is. Anyone who uses these types of arguments, okay? Okay, and here's an example of that. Here we have a crane lifting magnetically a bunch of iron, a bunch of metal, okay? Does that guy know exactly how a magnetic field works, how it attracts? No, he doesn't have to. All he needs to do is be able to use what he's already proven through experiment in the lab. In other words, someone goes to the lab, uses a magnet to pick up things, they make it stronger, okay? And once it's strong, they say, well, I need a stronger one for this. They get you a stronger one, they manufacture it, they learn how to manufacture it. No one in the entire line knows what a magnetic field is or how it does its magic from afar. Why? Because they can't see it or touch it. And so they don't even have speculations as far as magnets. So this is the same thing with quantum mechanics. Quantum mechanics, we didn't develop the computer because of quantum mechanics. I worked in the industry for many years, and we developed the chip by trial and error. In fact, they're improving the chips every day. Do you think those guys go in there and say, oh, we have so many positive carriers here and so many negative carriers there? In general, what they do, they do have an understanding of that stuff. No doubt about that. But what they do, they test things out every day, and they say, well, we put too much boron here, we put too much phosphorus over here, or whatever. And so they play around until they get it right. That's it. Did Edison know anything about electricity? No. In fact, we give him too much credit. Thomas Edison was a businessman. That's all he was. He wasn't anything beyond that. All he did was have his people, maybe he himself participated, developed the filament until they got it right. They got a long-lasting filament, and they sold it. And they did all kinds of contracts with companies, with Morgan, etc., and they built General Electric, and they moved forward. Was he a scientist? Absolutely not. He had no idea what electricity is. Okay, he died not knowing what electricity is. So, yeah, it's trial and error. And so to think that an experiment proves your theory, or to think that technology, the fact that we develop technology, proves the theory, the physical interpretation, the explanation, the mechanism. No, absolutely not. One thing has nothing to do with the other. And I always mention, you know, the nuclear bomb, you know, the atomic bomb. People say, oh, all these quantum guys, you know, they developed the atom bomb. All that math, you know. Well, the Iranians today know all the math that the West knows. They don't have a bomb. Okay, so I hope that sinks in. Okay, so how does Al-Khalili start his presentation? Well, he quotes Richard Feynman. And he only gives one quote from Richard Feynman. I'm going to quote a couple more because I want to drive home the point that these guys have no understanding whatsoever of the causes, the mechanisms. And you're going to hear from the horse's mouth here. It's going to be Richard Feynman talking from his grave right here, okay? So these are from his lectures, okay? And so here's what Feynman says in one of his lectures, Volume 1, Chapter 37. You can look it up. Quantum mechanics is the description, not an explanation, description of the behavior of matter in all its details, and in particular of the happenings on an atomic scale, okay? Things on a very small scale behave, talking about behave, okay, not causes, behave like nothing that you have any direct experience about. Yes, yeah, we do have experience. The problem is that you never thought, dear Richard, what could be mediating all this stuff. You were thinking of particles, and you cannot explain anything with particles, and therefore, you know, if you keep insisting on particles after 10,000 years, well, you got a mental problem. That's the issue, okay? They do not behave like waves. They do not behave like particles. Exactly. They do not behave like clouds or billiard boards or weights on springs or like anything that you ever seen mediated by particles. That's the part that was missing in Feynman's talk, in his presentation. Okay, so Feynman moves on and he makes this other statement. All these statements come from him, and it just shows you that they have no clue whatsoever. I hope I'm still on. I've had some problems here and there. I think I am. Okay, let me know if there's a problem. Okay. Again, YouTube had some kind of problem. I was going to complain, and somebody else beat me to it. Apparently, they say they're working on that type of problem. Some error that we're all getting. Okay, it says, this is from Feynman again. Newton thought that light was made up of particles. Particles, particles, particles. Particle man, particle man. But then it was discovered, as we have seen here. Okay, thank you, Tesla. But then it was discovered, as we've seen here, that it behaves like a wave. Okay, so it does or doesn't behave like a wave. It does or does not behave like a particle. Well, we keep going back and forth, right? Later, however, in the beginning of the 20th century, it was found that light did indeed sometimes behave like a particle. Okay, historically, the electron, for example, was thought to behave like a particle, and then it was found that in many respects, it behaved like a wave. Okay, so it really behaves like neither. Now we have given up. They've thrown in the towel. Okay, they have no idea how light behaves or how the electron behaves. Okay, and these are things that quantum supposedly is an expert at, right? We say it is like neither. So we don't know if it's like both or like neither. Okay, so I want you to keep track of all this. This is Feynman. He was a Nobel Prize 1965, I think. Okay, and a couple more. In this chapter, we shall tackle immediately the basic element of the mysterious behavior in its most strange form. Okay, we choose to examine. Listen to this is the one that Jim Al-Khalili quoted. Okay, we choose to examine a phenomenon which is impossible. Absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. And again, he cannot explain it with particles. That's the issue. You cannot explain it with quantum, okay, packets or whatever. In reality, it contains the only mystery. We cannot make the mystery go away by explaining how it works. In other words, he can't explain how it works, okay? We will just tell you how it works. He's going to describe. He's going to describe what they did in the lab and what they couldn't see. So he's going to infer what he couldn't see, and always the inference turns out to be particles. Now maybe at this point they should have said, hey, we got to quit the particle. Do you think it even crossed their minds for a second that They could think of something else, that it wasn't wave or particle. This is the issue, okay? I'm telling you how it works. We will have, in telling you how it works, we will have told you about the basic peculiarities of all quantum mechanics, okay? And here we have one more. Here he says the complete theory of quantum, again, theory. That's not a theory. If he's just going to describe it, it's not a theory. Theory is give me an explanation of a mechanism of quantum mechanics which we now use to describe atoms. A theory to describe. You see how they use these words. They don't know the difference between a description and an explanation. And in fact, all matter depends on the correctness of the uncertainty principle. Since quantum mechanics, listen to this, since quantum mechanics is such a successful theory, yeah, it's always successful. When you have the wolves guarding the sheep, it's always going to be successful. And all these people, you know, they block everyone who questions the physical interpretation. They don't even allow those things printed in their magazines, which are, you know, the respectable journals, right? Since quantum mechanics is such a successful theory, our belief in the uncertainty principle is reinforced, okay? But if a way to beat the uncertainty principle were ever discovered, quantum mechanics would give inconsistent results and would have to be discarded as a valid theory of nature. Oh, so all he wants is for me to destroy the idiotic, the irrational uncertainty principle? Hey, it's a piece of cake. Here, let me explain it to you. Here's a ball, right? I have no place to put it. When the ball is moving, it doesn't stand still. And when the ball stands still, it doesn't move. So the more you know about its position, the less you know about its momentum. And the more you know about its momentum, the less you know about its position. Now, how intelligent was Werner Heisenberg, okay? And of course, his buddy Bohr, you know, said, hey, you come up with that nonsense and I'll give you a Nobel Prize. And they just kept giving Nobel Prizes to each other. And yeah, so Werner Heisenberg, he said, yeah, when the ball moves, it doesn't stand still. And when it stands still, it doesn't move. And he can't get him to do both at the same time. Oh, my God. This world, Mother Nature is so cruel. Okay, yeah, Heisenberg's uncertainty principle is absolute nonsense, and he says it's the foundation of quantum mechanics. Okay, last one here, also from Feynman. He says, one might like to ask, how does it work? What is the machinery behind the law? Yeah, that's what mechanisms. That's what we want to know. No one has found any machinery behind the law. No one can explain any more than we have just explained, quotations. No one will give you any deeper representation of the situation. We have no idea about a more basic mechanism from which these results can be deduced. That's the status. 60 years later, Al-Khalili says exactly the same thing. He says, we have no idea, we don't know. But they've proven it. Quantum has been certified as the most accurate, most successful theory, but they don't know. Now you tell me how much sense that makes. We have a problem. We got to find out what the problem is. How can on the one hand they tell the public, you know, we don't understand all this stuff, and then on the other say, oh, we've proven it. It's more accurate than anything else we've had. It's been, we've confirmed it. We got a big problem. We got a problem because these people are giving us the runaround with their double talk. We need to find out where the problem is. Okay, so let's move on here. What is the What is the slit experiment? Let's give you an idea. So what Al-Khalili is going to try to explain is the slit experiment, the one that drives the quantum mechanics all nuts. Okay, and here it is. Just very simple. You shine a light through two slits. What do you expect to see on the screen? Well, you would think that if you shine a light, okay, you would see maybe two little shadows there. Okay, this is what one would expect. You shine them through two little screens, like two windows, and you should see maybe a shadow of the windows, right? Something like that, okay? And instead what they see, okay, is this. They see fringes. They see many shadows or many lights or whatever. It's like if light broke apart and just went in different directions. Okay, so this is the problem. Okay, and so what do the mechanics have in mind? People like Al-Khalili. Okay, well, what they have in mind is what this guy illustrates. He's from one of the universities. And what they have in mind is what Einstein and Bohr discussed in 1927 at the fifth Solvay Conference. Okay, and it goes like this. Essentially, the source shoots a particle that hits or strikes the slit, the partition. Okay, and so it hits it and bounces inwards. And then the other one bounces off the other slit and bounces outwards or inwards. In other words, they're all bouncing in against and going into the screen. That's how these people see it with photons. They also see it like this with electrons. Okay. What is the problem with this? And again, I should mention one more time that Einstein and Bohr discussed this same thing, and they said, well, you know, if the photon hits the partition, you know, hits the little window seal and pushes the partition over, well, then we have a problem with the uncertainty principle, because now you can't tell where the partition is, because now it's moved, because you have this photon hitting it. Okay, so they discussed this hours between Bohr and Einstein in 1927. Today, even to today, everybody's discussing these things, and they never reach a solution to all these question, because again, they're doing it with particles or with waves. That's the problem. Okay, so here is a little trick that I play on them. I'm going to remove the slits. Okay, I'm going to leave only the center. I'm going to put a needle instead of slits. Okay, now what is it? What is the photon bouncing against to come inwards? Okay, you see what the problem is? This would create a serious problem for quantum, because quantum is saying, hey, it bounces and comes inwards. That's the way they see it. And it turns out that now I remove the slits, and all I left is a needle. You can also do this with a human hair. In fact, just to make sure that you understand, I'm not claiming responsibility for that. I'm saying that good old Newton, he puts it in his book of optics, and he says he used his hair and saw shadows. And the reason I found out about this as well is that Thomas Young, in his second experiment, used Newton's hair experiment. Okay, he did it the same way. He said, look, he measured, the fringes with by putting a human hair. So you do not need the slit. Okay, you can do it with hair or with a needle. In fact, here it is. I did this experiment a few years ago, and you go all the way to the end and you'll see the fringes, okay, on the wall. That's what it looks like. You can do it in the comfort of your house. Just get a laser pointer. It's got to be monochromatic light. And you do what I did here. I'm going to show it in a second here. You're going to see that there's going to be a needle mounted on a chair. Very expensive, very dangerous experiment. Always do it in the presence of a trained relativist. Okay, and there you see this the fringes on the wall. Okay, so don't take my word for it. Just buy yourself a laser pointer. Get yourself a needle. Okay, and you'll be able to do this experiment. Okay, and here it is. I'll change my hands, I'm right-handed, okay? Here's a needle, just stuck to a cork, okay? And I'm just gonna put white light, okay? Just shine it on there. Here, the other one is the red one, but you don't see that one, okay? Anyways, just point it, have them fixed, do it against the wall, you'll see the fringes. You don't need slits, you don't need to do it the way they do it in college, those advanced people, those mommy's boys. No, you can do it at home. You can do it at home, just point, laser pointer, to a needle, and you'll see fringes on the wall. Do you need to know distance? Do you need to know the speed of light? Do you need to know any math? No, you need to explain why you see the damn fringes on the wall. That's a physical phenomenon. You don't need any math. You don't need any distance. You don't need to measure anything. You don't need to use the little d's and the little a's and the little x's. None of that. You don't need any equations. Just point it, get the fringes. Once you see the fringes, say, how does Mother Nature do this trick? It's a qualitative answer. Okay? Very simple. You just got to explain it. Okay? Okay? And where was the problem? Well, one of the big problems is that the mathematicians never discovered that there's a third kind of wave. Okay, all of them go to college, they get their PhDs, they only learned about two waves. They learned about these two waves, okay, the longitudinal and transverse wave. They never learned there's something called a torsion wave. Okay, in fact, they dismissed torsions, I don't know for what reason, okay, because that's what light is. Light is not a longitudinal wave like sound is. It's not a transverse wave for sure. It doesn't go up and down. And by the way, what you're staring at as far as the transverse wave is concerned, what you're staring at is a bunch of vectors. Those arrows, those are not engine arrows. Those are vectors, okay? And what you have is a ridiculous mathematical contraption. You can call it a mathematical object where you have vectors moving, you know, from A to B. What sense does that make? Okay? Torsion, well, for that you need a rope. Okay? You can produce it with a rope, for example. Okay? You can do it with a chain. Any elongated object, you can do it. Okay? That's what we're going to propose. Okay? And so here's the difference between quantum and the rope hypothesis, which is what we propose here. Mathematical physics, you have all discrete particles. The rope hypothesis, all atoms in the universe are interconnected. By what? By what we call the electromagnetic rope. All atoms are physically connected. Okay, so that's the proposal. Okay, and with that, we're going to explain the slit experiment very easily. Okay, and so first, let's get an idea of what light is. Is light a bunch of particles? Is it a bunch of waves, or is it torsion between two atoms that are united or bound to each other by the electromagnetic rope? So you have the quantum jump there. Atom is pumping back and forth. That's the quantum jump that good old Mr. Bohr discovered. Even though he got the wrong interpretation, he said it's the little electron bead that jumps back and forth for no reason whatsoever. How that electron bead was tied to the nucleus, he never explained. Even to this day, they have no explanation for that. Here, it's very simple. You know, the threads make up the atoms themselves. And those who've seen the previous videos know what I'm talking about. I'm not going to go over that again. All I'm saying here, we have comparison of the different mechanisms proposed. Quantum mechanics proposes the two upper ones. Rope model proposes the bottom one. We have atoms pumping back and forth, little hearts that are pumping torsion waves through the electromagnetic rope to other atoms in the universe. That's the model we're going to use. Okay. Okay, and so how do we explain the slit experiment with this thing, with this rope, with these atoms, interconnected atoms? Okay, here we have the lights out, okay, and we have the ropes are already connected. Remember, all atoms are interconnected. Okay, so the ropes are already there, are in place. Okay, all we do when we turn on the laser light, okay, is we stimulate those existing ropes, okay? The atoms that are connecting the source to the slit, for example, in this case, and from the slit to the screen. And what you have is all those ropes are now torquing faster, okay? Because the atoms are pumping faster. That's what the increase in frequency does. It shortens the lengths of the rope. So the lengths of the rope are now shorter. That's why it comes within the visible range, okay? And here's another vision of this, sideways, I guess. This is where the light's turned off, okay? What happens when we turn the lights on? We're just going to go in two steps here. First, we're going to look at what happens to the ropes that are connected from the source to the slit, okay? You can see they're turned on, okay? Why? Because they're at a higher frequency, okay? And now let's look at the full picture, and that's now the, let me get that up there. Okay, so now you see the fringes. Why? Because you have these ropes that are suddenly torquing at a higher frequency. In other words, shorter lengths of the ropes, and they're going to interfere with each other. Okay, what do I mean by interference? Well, now it's standard wave interference, both constructive and destructive. Here you have a picture of that, okay? Let me get back in here. Okay, and what you see is, when the ropes are in phase, then you have constructive interference. When the ropes are out of phase, the links, are out of phase, then you have destructive interference. And then at the bottom you see that there's, you can have different angles. That's why you have a, nuanced fringes. I mean, if you could really see all those little that, you would see that there are the fringes don't go directly all the way to black, to darkness. No, there's fringes all the way from one fringe to another, but all those fringes are different tones or different strengths, okay? And that's explained by the fact that you have different angles of the rope, okay? So we do have an explanation for that. And again, it's all, those who studied wave mechanics, this is nothing new to them, okay? It's just wave mechanics applied to a rope, to a real physical object, not like in mathematics where they use waves, which are vectors, and particles, which are zero-dimensional and go backwards in time and come out of the void and all that nonsense, okay? Now, this is all rational, okay? Rational, why? Because you can make a picture of it, you can illustrate it, okay? And because you can simulate it. And this is, again, a different picture. You can see constructive and destructive interference, more or less how they look. This is the way they end up on the screen. If the two ropes one coming from one slit and the other one from the other, or from the two sides of opposite sides of the needle, right? When they meet, if they're in sync or in phase, then you have constructive interference. And if they're out of phase, you have destructive. Very simple. Let me give you a dynamic version of this. Okay, this is the dynamic version. Let's hope you understand it. It's not. You got to get used to this. Okay, the top one, the lights are turned off. What do you see there? Well, if you compare the top one with the middle one, the before turning light and the bright band, you'll see that the rope, it has shorter links in the middle. The one in the bright band has shorter links. That's what the difference is between those two, okay? So the first one, it's below the frequency that we can see, okay? So it's just, or it's a shadow, essentially. And now you turn on the light, what happens? Suddenly you turn on the light and the frequency goes up, and now the atoms are pumping faster and wider, either or both. I still haven't figured that one out completely, okay? But that's for theorists also to put their heads here. And it's either the atom is pumping to a larger balloon. Those are the famous orbitals of quantum mechanics. They're actually balloons, okay? And these balloons are pumping back and forth, okay? They're quantum jumping there. And if they pump very high, obviously they're going to torque the rope to a higher frequency, and because of that, it stimulates the atom at the other end, both at the slit and at the screen, okay? And then the one at the bottom shows you destructive interference. The difference between the middle one and the one at the bottom, if you look at the ropes on the left-hand side, the two ropes in the middle, they are in sync, they're in phase. The two ropes on the bottom left, they're out of sync. That's what I'm illustrating there, okay? And that's essentially the mechanism proposed for the slit experiment. So we do have a rational explanation, okay? It's this is just an introduction, okay? People have a million questions after this always, and I've discussed those in our conferences. We had the one in Buenos Aires, what was it, 2017, and I discussed the slit experiment there with the folks. Obviously, my presentation was on the basics, and then if you have 1,000 questions, as people usually do, well, then that's when we get some beers and we discuss the finer details, okay? So this is just an introduction so that you get the idea, the mechanism. What are we proposing? Okay, you can see that whereas quantum mechanics says, oh, it's beyond imagination, nothing we can imagine can explain it. Well, here we have something that is imaginable. Okay, you have essentially, here we have my little rope, one of the ropes. I got a bigger one, a little smaller one. Okay, if the see if I get this right. If one is side, let's see this one. If one is up and down, the other one is sideways. Okay, right. One is north-south, the other one is east-west. That's destructive interference. If they're both, you know, if they're both north-south, for example, then you have constructive interference. We're done. That's how simple it was all these years. Just in case, entanglement, oh, that's a hard one. That's a really tough one. It's for babies. Here's entanglement. Entanglement means that if something is clockwise over here, it's counterclockwise at the other end. And if you switch this one to counterclockwise, the other one is now clockwise. Okay, okay, here it is, very simple. Okay, from my end, I'm going to twirl it clockwise. Hopefully in your end, it's going counterclockwise. Okay, Mother Nature understands counterclockwise and clockwise. She doesn't understand positive, negative, north, south, all that garbage from math. She doesn't understand that. She understands physics. Physics is clockwise, counterclockwise. Okay, so now I'm going to turn this mine counterclockwise. Hopefully yours is twirling clockwise. Okay? Simple. So difficult, so many years, unimaginable. And yeah, if the rope extends from the Andromeda galaxy 2.2 million light years away, okay, to the Earth, well, that rope can go this way or it can go that way. And people say, well, how about when we immediately turn in this one counterclockwise? You know, it's going clockwise. Okay, fine. Now we'll turn it counterclockwise. Does that rope all the way to the Andromeda galaxy completely turn in the opposite direction? There's several answers to that. I'll just give you one to ponder, okay? This is important for you to think in these terms. The mechanics, the quantum mechanics, they have no idea what they're doing in the lab. Okay, we saw Mr. Tonomura there saying that he handled one electron at a time, and we showed him that no, that he wasn't handling one electron at a time the other day. And if he thinks that he handled one electron at a time, and that's what he published, and that's what the mathematicians think, when obviously if an electron is a balloon that encapsulates the proton star, then he can't handle that one at a time like a little bead that's rolling around the atom. Those are two different notions. See, these people are saying, oh, I handled one electron at a time because he's got some kind of electricity moving there, and his idea of electricity is a little bead that moves from atom to atom. But if that ain't what he's seeing, in other words, that's not the real world, then he's not handling one electron at a time. And if he can't handle one electron at a time, much less can he handle a photon at a time, which is what all these people claim. I think Aspect, when he ran his experiment, I don't know if he got a Nobel Prize for that, but a French guy, he did the EPR experiment, okay? And he said, oh, he proved it. He proved that what Einstein said was impossible. EPR, Einstein, Pulaski, Rosen, you know, they said it's impossible. These guys were able to do the experiment, okay? But if he thinks that he handled one electron or one photon at a time, well, he's crazy. Because there is no such thing as a photon. Photon is just a link of the rope. That's what it is. That's what they've been thinking, it's a particle all these years, okay? And so, yeah, they think that a particle is moving. And so they say, well, is the particle moving at the speed of thought from the Earth to Andromeda? Well, we need to figure out under the rope model what these people are doing. We need to find out if they're actually torquing the same rope. Okay, they could be torquing a parallel rope for all we know, because right now they don't even know what they have. They can't see in that world, so they have no explanation. They think they're moving one photon at a time. They think they're moving one electron at a time. If photons and electrons are not particles, we have to redo the whole thing. We got to erase the board completely and start all over again and fire all mathematical physicists from science. We got to get rid of them, all of them. So anyone who's got a degree in mathematical physics has to get out. For sure he has a deranged mind. Okay? So we don't know what they're doing. That's the first answer. There's more answers than that, okay? Okay, so where does this take us? Here. If this is correct, if this is what Mother Nature's doing, she's doing it with the electromagnetic rope, all atoms are interconnected, physically interconnected, well, then we have a solution also to Arthur Eddington's warpage of space. It's not done by light curving around the so-called gravity well of the sun, no such nonsense. No, it's that the star at the far end that we are able to see behind the sun during an eclipse, it's photons. In other words, there's no photon traveling. It's rope connected from one atom to the corona of the sun is being relayed. That same frequency is being relayed to your eyes or to whatever source, target you have there. That's it. So it's done with straight lines. Light never travels in curves. The way light curves is by having a bunch of straight ropes forming what appears to be a curve. Okay, that's why we can see around corners. We have all this refraction and reflection going on. What is it? Just signals going along taut ropes. Rope is always straight as an arrow, or even straighter, I guess. Okay, and yeah, so this would give you an idea that that both these experiments, if I can get this up here, okay, both these experiments are the same. Let me get it back up here. Where did I put this now? Here it goes. Both these experiments are the same. In other words, the slit experiment on the right and the gravity well, the warping of light, the bending of light as they call it, are the same experiment. Okay? They're both essentially the same thing. What you have is relaying through electromagnetic ropes. Okay, so let's give you the summary. And I don't know if to call them alkali or alcohol maybe, I don't know. Here it is, Mr. Alcohol. Okay, and so what are conclusions or a summary for Mr. Al-Khalili? Well, Al-Khalili and his buddies, the mechanics, have no idea how Mother Nature does the slit experiment. Okay, I think Feynman, even Al-Khalili, 60 years later, he's saying exactly the same thing. Okay, in vain and against all odds, Al-Khalili and Alkali and his buddies continue to explain the slit experiment with particles. That's where the problem is. The mechanics do not understand the difference between an explanation and a description. Not a single mathematical physicist on planet Earth understands the difference between a description and an explanation. They use these words, sometimes they use them in different contexts, but later on they talk about explanations when they have absolutely no explanation in all of mathematical physics for what? For the invisible mechanisms of Mother Nature. Not one. Why? Because they do them all with particles. And light is mediated by neither waves nor particles, but by a pair of twined threads, a DNA-like rope. And unlike slow, one-way, zigzagging longitudinal and transverse waves, a torsion propagating along a taut rope spins in situ, bidirectionally, rectilinearly, and very fast. The rope explains the slit experiment with flying colors. We have no problem with the slit experiment or with entanglement. Okay. So what are the questions people typically ask? I'll ask them because I already know what people ask. Okay, I've had 20 years of this, people just asking the same questions. And the main one, I'm just going to deal with the main one here. Main one is, how come we can't see or touch these ropes, these electromagnetic ropes? Let's go to the lab. Show me, prove to me, demonstrate their existence. Okay, so let's answer these these individuals. Okay, what is the answer to all that? Okay, so let's go over that. These are the answers. Okay, we start with the first one, and the way we do it is we read to them by the book, the Miranda rights. That's what we're gonna read to them. The golden principle of physics, which they never learned. Not a single mathematical physicist, so-called physicist, ever learned in his life. Okay, he never learned it. He never learned it in high school. He didn't learn it in college. He didn't learn it when he graduated. He didn't learn it when he did, experiments or whatever, or in his work, professional work. Physics requires an object. You can't do physics without an object. Okay, I don't know how much to enforce that, to rub that in, for people to memorize it. Okay, you can't do physics without an object. If we wipe out all matter from the universe, there is nothing there, not a single, not space made of particles, but space made of space. Nothing, absolute nothing. What is nothing? That which has no shape. Right? That's nothing. That's the definition of the word nothing. That's the definition of space, which is a synonym of nothing. If you have absolutely nothing, there is nothing going on. Nothing is happening. There is no phenomenon. So whenever there's a phenomenon, there had better be an object. You better have an object. What is an object? That which has shape. Okay? An object is not what the mathematicians have used all these years. Okay? Here it is, the rundown, because this is what people raise as answers to that question. What is an object? Well, this is what an object is not, okay? And until you get this underneath your belt, you don't know the first thing about physics, okay? An object is not that which we can see, that we can touch, that has mass, that has volume, that moves or can move, is made of parts, is visualized through time, that we can use in a sentence, that has color, that exists, is 3D, is not standalone. And I don't know how many more. These are the ones that I've collected over the years, because people come up with all this nonsense. This is what they think an object is. Where do they get this? From ordinary speech. They go to the dictionary and say, well, this is what it says here in the dictionary. It says an object is that which I can see and touch. That's the typical definition. And that's the one used by mathematical physicists. And that's why they say, let's go to the lab and let's see if we can see or touch the rope. That's what they want. They want to see or touch. They want proof. They want evidence. Which means that they have not the slightest idea of what the scientific method is about, okay, or physics. Physics is an explanation of a mechanism. Mother Nature deliberately, God, Father Universe, one of those guys, maybe the devil, one of those guys with his superpowers made light, gravity, magnetism, invisible and intangible, unhearable, untastable, unsmellable. You can't go to the lab, run an experiment, to see, touch? What are you going to find out? You want to know gravity? Hey, very simple. Here's gravity. Okay, you let go of the ball, and it falls to the floor. That's the only experiment you ever needed. Now you got to explain it. No more experiments. We're done with experiments. Now we need to figure out how gravity is done, how light is done, how magnetism is done, how electricity is done, how the atom does its quantum jump. We have to figure it, what it looks like also. We got to figure out these things, and you're not going to figure them out by running an experiment. You're going to figure them out by getting a beer, closing your eyes, moving your head back, and visualizing. You have to imagine how Mother Nature might be doing that with objects, because she better be using some kind of object. What is an object? That which you can touch or see? No, it's that which has shape. And the rope obviously has shape, okay? In fact, here it is. I'll show it to you. That's the difference between the ridiculous thing that James Maxwell proposed, a bunch of vectors moving through space, okay? And of course they didn't know what it is, so some people say it's the undulation of nothing, others say it's the undulation of who knows what, of particles. They don't know, they have no idea. But the rope, you know what a rope is. It's got two threads, twined threads, we're done. So what they've been staring at all these years, what they thought they've been staring at, they thought it was a wave, a two-dimensional flat wave, no, it's a three-dimensional rope. That's what they've been staring at. And the rope interconnects any two atoms. When the atoms pump, the rope torques. We're done. That's how simple it was. We live in a very, very simple universe. Two atoms bound by a rope. That's the model. That's the simplest model you can think of. Simple and symmetric, by the way, okay? Okay, so yeah, the issue there is the definition of the word object. The word object is not that which we can see or touch, it's that which has shape, okay? Okay, there it is. An object is not see, touch, mass, volume. An object is none of those on the left-hand side. An object is that which has shape. It's got to be a standalone object. It should be the only object in the universe when you present it in physics. You point to it and say, table. That's the only table in the universe at that moment in time, when you name it. Only then can the ET, the visitor from outer space, the Klingon, understand your language and say, okay, table refers to that object there that he pointed to. Now you can use it for anything you want in your theory because you've identified the object. And that's the way it works. And obviously quantum mechanics cannot do that. What are they going to point to for a wave? What are they going to point to for a wave packet? Corkscrew? So this is the issue. The issue is these people have no objects. They have only mathematical objects.